Hello, welcome everyone. Today we will continue discussing on those carbon-carbon bond formation reactions. As we were discussing, these are truly the greatest discovery of the organometallic chemistry. It has revolutionized the way the carbon-carbon bond can be formed. Since carbon-carbon bond is fundamental or the backbone of organic compounds, to be able to synthesize these carbon-carbon bond in a controlled fashion is of paramount importance. We have named those reactions, we have seen those named reactions mainly based on the reagent that is used. The same carbon-carbon bond formation reactions are named differently. For example, as we have seen in the last class, if aryl halide, usually aryl halide is the one coupling partner, aryl halide such as aryl bromide, chloride, iodide or even aryl diazonium salt, aryl OTF, mesylate, nonaflate or whatever it is, if your electrophile is aryl halide, keeping that as constant, if we have the other partner, so to speak, the transmetallitic reagent is differing, then the name reaction will appear, various name reaction will appear. For example, if the transmetallitic agent is aryl boronic acid or any boron partner, then that reaction is called the Suzuki reaction. If it is a Steen reagent, of course, aryl halide is constant, that reaction is called Stille coupling. If it is zinc reagent that is used for transmetallation, that will be called Nigisi reaction. If we do have silicon as a transmetallating reagent, organosilicon reagent is used, that reaction will be called the Hiyama reaction. If it is lithium or magnesium reagent is used, then those reaction will be called Kumada reaction, okay, or Kumada coupling reaction. Now, in the last class we have seen some examples of Kumada coupling. We have started discussing also about the Suzuki reaction. We have seen the beautiful example of the Suzuki reaction where even sp2 halide such as alkynyl halide was reacted with alkynyl boronic acid to give you the sp2 coupling, where two alkynyl partners can be associated to form the carbon-carbon bond. These reactions are extremely successful and extremely valuable. Okay. As we were discussing, the stereo centers remain intact, or the stereo control is given or is controlled by the starting materials. Also, another very important feature of the Suzuki reaction is you can have wide functional group into your two partners and the reaction will proceed smoothly without any problem with the functional group. As we were discussing for Kumada coupling, where organolithium or organomagnesium or Grignard reagent are used, the problem could be the functional group tolerance. If you have functional group that is incompatible with the Grignard reagent, those reaction will be problematic. But for Suzuki reaction, no such problem appears and it works beautifully like a champ. Now, today we will continue discussing on the functional group tolerance of the Suzuki reaction and also the carbonylative Suzuki reaction. Let us first discuss one functional group tolerance, where we will see in presence of acidic functional group how Suzuki reaction is working beautifully. Okay. So, first we will take an example where we will see that the reactions are occurring in presence of acidic functional group. So, this is again continuation on Suzuki reaction. The example that we have in hand is OTF these are acidic of course. Now, if you want to react with aryl boronic acid, the aryl group can be also having different functional group in presence of palladium tetrakish. We will get the product that we are looking for, the desired carbon-carbon bond formation between the aryl group and this carbon center. This carbon center and the carbon center of aryl group forms the bond to give you the desired product. And the yield for these reactions are usually very high, 74% to 94%, and no racemization. That is very important because you have a stereo center at this site, we do not get any racemization. So, that is a very beautiful thing, one should be very proud of that from the Suzuki reaction. Now, for the Suzuki reaction also we know that there are variety of coupling partner that can be utilized during these reactions. For example, we can have alkynyl coupling partner, for example, alkynyl halide as well as boronic acid. In between, if we are to insert or we are interested in having a carbonyl in between the halide partner as well as the boronic acid partner, we can have the carbonylative Suzuki coupling to give the ketone compound. That is again a powerful reaction. Let us say for example, if one is interested in synthesizing benzophenone. So, one of the aryl halide and aryl boronic acid you want to put in between carbonyl. So, that can be done. That is a beautiful example of a Suzuki reaction. Another problematic coupling partner could be alkynyl halide along with aliphatic aryl boronic acid, aliphatic boronic acid, and then you have a carbonyl in between. Indeed, those reaction even works quite beautifully for the Suzuki reaction. Let us look at one of the example of this carbonylative Suzuki reaction where carbon monoxide is used in conjunction with the traditional coupling partner of the Suzuki reaction. Okay. Carbonylative Suzuki reaction. Carbonylative coupling. Okay. Now, what we have in hand is an alkyl halide such as this one, and we have an aliphatic coupling partner. Again, these are usually traditionally difficult coupling partner because in sp3 carbon center is there and you can get a predominantly other side product that might be happening in these cases. But palladium PPH3,4, that is palladium tetrakish, usually referred as in presence of potassium phosphate as a base. We do not need stronger base, potassium phosphate is good enough. We do see that your carbonyl group is getting incorporated. So, this carbonyl group is the same over here and it is getting incorporated. Overall, you can synthesize this octyl boron reagent starting from HBr2 and reacting with your olefin reagent, corresponding olefin reagent. Okay. Now, if you look at carefully, what we have seen right now is a alkynyl coupling partner and alkynyl halide, that is a very challenging coupling partner, along with alkyl boronic acid reagent or boron reagent, alkyl boron reagent. These two partners put together in between carbon monoxide is placed. Well, that is a very reliable way to synthesize any ketone compound. You can have diaryl ketone, you can have dialkyl ketone, you can have alkynyl alkyl ketone. These are very, very interesting compound, and specifically if you are looking to synthesize a bigger molecule which has ketone in it. Of course, there are plenty of natural product with ketone moiety and plenty of pharmaceutical, industrial applicable molecule, industrially important molecule that has ketone unit in the molecule, and these compounds can potentially be synthesized for corresponding coupling partner for the Suzuki reaction. So, that is actually giving us a lot of control into the ketone formation. Let us look at the mechanism briefly. Of course, it is a simple mechanism, but let us look at anyway. That will give us a good feeling that how this reaction will be proceeding. Okay. So, it occurs via a palladium iodo and alkynyl unit. Of course, you have reacted CO. What you get over first is CO coordination with the palladium, and eventually you will get palladium iodo with a CO in there, from wherein you will get transmetallation and reductive elimination to give you the product. Okay. And this is nearly 90% yield. So, what we have seen that alkynyl halide will undergo oxidative addition to give the palladium iodo and alkynyl unit. Now, carbon monoxide will then come and interact with metal center to give the metal carbonyl bound alkynyl iodo compound. From there on, carbon monoxide will insert in between the palladium carbon bond of the alkynyl unit to give the acyl type of intermediate. So, alkynyl CO palladium intermediate, and iodo is of course attached to it palladium. Subsequently, what will happen, as you know, transmetallation from the boronate or aryl boron partner or alkyl boron in this case will come. Transmetallation in presence of a base will happen to give rise to the intermediate, from which reductive elimination will give the desired product, and as you have seen, the yield for these reactions are quite good. So, essentially what we have seen so far, that Suzuki reaction is quite versatile. It can tolerate various functional groups, it can even tolerate an enantiomer, or stereocenter can be retained during the process. We have seen also the also not only the stereocenter, also the geometry, stereo control you can have if you are starting with a trans olefin or trans alkynyl halide, you will end up with the same compound or without changing the geometry at the coupling partner. So, as you have seen, two alkynyl halide, one alkynyl halide and another alkynyl boron reagent, giving you the control completely with respect to the reagent during the reaction, no racemization or isomerization of the partners or substituent is happening during the Suzuki reaction. And most importantly, any reaction that you can think of, anywhere any carbon-carbon center is there, you can split it into half, and one side could be halide, the other side could be the boron reagent. And if you want to put a palladium, for example, simple palladium tetrakis most often work. If you want to put them together, you can get it done in presence of a base under very mild condition and a standard organic solvent. You can usually get the product quite efficiently. This demonstrates the efficiency and the ease of the formation of this desired carbon-carbon product that one may be interested in. The problem with the Kumada coupling was the functional group intolerant. Kumada coupling is functional group intolerant because it is dealing with organolithium and your Grignard reagent. No such problem happens for this Suzuki reaction. In all these cases, usually we are using a compound or using a palladium compound which is in palladium 2+ oxidation state, but we are not interested in palladium in 2+ oxidation state. For the catalysis, we need palladium 0. So, one way or the other, usually by the help of or by taking the help from the starting material, for example, in the first case we have seen organolithium reagent or Grignard reagent will help form the palladium 0 from palladium 2, and that palladium 0 in situ formed will go on with the catalytic cycle to give you the oxidative addition, transmetallation and reductive elimination. So, once again, although we are using palladium 2 as the starting material, we need to have palladium 0 formation during the process, otherwise catalytic cycle will not go on. Usually for these standard carbon-carbon coupling reaction or carbon-carbon bond formation reaction, we have the starting material helping us out for palladium 0 formation. Then again the question, simple question is, why do not we use the palladium 0 directly from the market? Indeed, there are plenty of palladium 0 source that is available. The problem of those palladium 0 source which are commercially available is, in order to stabilize palladium 0, they need to have a ligand associated with palladium. Now, for your desired carbon coupling reaction, you need another palladium ligand complex, not the ligand that comes from the market. So, you need your desired phosphine ligand for example, to be associated with the Suzuki reaction or Kumada reaction. Now, that ligand, that special ligand of yours for your desired reaction may compete with the market available palladium 0 ligand. Now, since there is a competition, because the ligand has to be good in order to stabilize palladium 0 from the market. Now, your desired ligand and the ligand from the market for palladium 0 competes. So, your overall desired catalytic cycle can be problematic. Therefore, it is desirable that you start with palladium 2. Okay. Now, let us move on. Of course, we will come back with some more example in later classes for Suzuki reactions and the application of these, as we also have discussed that aryl halide coupling partner or the oxidative addition also is dependent on the type of substituent we have in the electrophile. If, for example, if you have a aryl bromide and those are ortho substituent there, 2 and 6 positions are having big or large substituent, then those reactions will be problematic because steric demand of the substrate slowed down the oxidative reaction. Similarly, if it is an electron rich substrate, we have problem during the oxidative addition. So, electron deficient substrate will be preferred. Now, when sometime you see that some reactions require very low loadings of palladium, low amount of palladium, even homeopathic amount of palladium will be good enough. Well, then you have to see whether it is really the catalyst control or the substrate control. If the substrate combination is the easier one, where your, let us say, aryl halide is electron deficient as well as the other partner is also electron deficient, and therefore reductive elimination is also faster as well as oxidative addition is also faster, those are not really the right reaction to compare, because those are supposed to give you a very good turnover number. But if the ligand is very efficient, then irrespective of the coupling partner, you are supposed to get a very good turnover number. That is why the ligand designing becomes very important. Now, of course, as you know, ligand plays a very important role for these carbon-carbon bond formation reaction, even for any organometallic reaction. If the ligand is way too bulky, then of course you have problem in oxidative addition. You need ligand which is electron rich. So, as you were seeing, the Suzuki reaction is quite compatible with a number of coupling partners. Irrespective of the coupling reaction, the name reaction of it, you need a ligand which is very good for your oxidative addition and reductive elimination. For oxidative addition to be facile, you need an electron rich ligand which will be also not too bulky. So, you need a smaller ligand, electron rich ligand. But on the other hand, for reductive elimination, what you need is a bulkier ligand because reductive elimination is going for a higher coordination number to a lower coordination number. So, bulkier ligand will push the two coupling partner together, and therefore, bulkier ligands will be very much promoting the reductive elimination. At the same time, you need to have a electron deficient ligand for reductive elimination, because from a higher oxidation state to a lower oxidation state metal is going. For oxidative addition, lower oxidation to higher oxidation state it is coming. So, palladium 0 going to palladium 2 for example. For reductive elimination, palladium 2 to palladium 1 is going, and therefore, the electron richness will be favored for the oxidative addition. For the reductive elimination, electron deficiency will be favored. Same way, for the oxidative addition, a smaller ligand will be preferred. For the reductive elimination, a bulkier ligand will be favored. Now, this is the dilemma. This is where the problem is for designing a ligand. How a ligand could be electron rich as well as electron deficient, how a ligand could be small as well as large. So, this is where the traditional problem comes, and people have tried to address it by many different ways. One of the approach that found to be very successful is to use this biphenyl phosphine ligand. Whenever biphenyl phosphine ligand need to be bulkier, the biphenyl unit coordinates or interacts with the metal center, so to speak palladium in this case, and whenever it need to be smaller, the biphenyl ring can swing away, and therefore, the palladium center is essentially looking at a smaller ligand. Both these ambivalent or bivalent characters, in one sense it is bulkier, in one sense it is smaller, is crucial for the ligand designing, and this remains a holy grail for the catalysis. Once again, for the catalytic cycle, you have oxidative addition, transmetallation and reductive elimination. The requirement for oxidative addition is completely opposite to that of the reductive elimination, and this is exactly the point where the ligand designing is so important, and there is no suitable ligand for a variety of reaction, because the requirement may change depending on the coupling partner. Nowadays, one of the ligand that has shown the best result irrespective of the coupling partner and the type of reaction we are looking at is that of a biaryl phosphine type of ligand, and there exist variation of those ligands which are found to be suitable for a number of reactions that is of interest both in industry and in academia. Next, we will briefly discuss the Nigisi reaction. Okay. Of course, Nigisi reaction means the zinc reagent will be used. The best part of the Nigisi reaction is these reactions are dependent on the zinc reagent, but zinc is not that nucleophilic compared to let us say organolithium or organo-Grignard reagent or RMGX, and therefore, functional group tolerance is going to be excellent for the Nigisi reaction. Let us try to look at the Nigisi reaction. What are the coupling partner and what is the efficiency of these reactions? Nigisi reaction. We have Rx and R prime Zn(x) that will give you catalytic in presence of palladium 0 to give you R and R prime. As we said, these are good functional group tolerance. If you have a bulky partner such as these, and you can get the desired product in presence of palladium 0 catalytic amount and this methyl reagent. This gives you 96% yield of the desired product. Now, of course, if these are very good for the coupling reactions, and not only that, we also would like to have the reaction where maybe let us say Kumada reaction is failing. For example, a ketone synthesis, if you have a acid chloride and you are reacting with zinc reagent, that means Nigisi reaction, you can get the corresponding ketone product. On the other hand, if the same reaction one is interested in doing under the organolithium or organomagnesium reagent or Grignard reagent, so to speak Kumada coupling, those reaction will not be successful because they might will lead to the tertiary alcohol formation, one more addition on the desired product. Let us look at one of those example. RCOCl, let us say R is methyl and reacting with chloro zinc butyl and in presence of palladium tetrakis, it gives 80% yield of RCO butyl. Okay. So, this particular reagent where a ketone is formed starting from acid chloride and the organozinc reagent is going to be successful and can give good yield, but the same reaction will not be successful for the Kumada coupling reaction. Now, this demonstrates the functional group tolerance of Nigisi reaction. Zinc, aryl zinc or organozinc reagent is used once again for Nigisi reaction. One can have plenty of reaction or any reaction of their choice if they are ready to use this zinc reagent, and functional group tolerance is is uncomparable. It is almost every functional group can be tolerated under the reaction condition. Reaction conditions are usually mild and therefore, desired product can be formed very easily. So far we have seen Kumada coupling, Suzuki coupling and Nigisi coupling. In the next class, we will briefly discuss the Stille reaction, the good things and the bad thing, pros and cons of Stille reaction, and then also we would like to discuss what happens when alkyl halide were used, why alkyl halides are very tough problem in the carbon-carbon bond formation reaction. All these issues can be solved by suitably designed ligand, because ligand plays the most crucial role during these processes. With those discussions, we will be coming in the next class of those carbon-carbon bond formation reactions. It is also most important for all of us to appreciate and understand the value ligand holds for these coupling reactions. Ligand is most crucial to cut down the cost, although ligand itself can be little expensive, but compared to other things that is involved in the process, even the ligand is expensive. If we can cut down the palladium, because palladium loading is most important to cut down, because if during the processes, let us say for a medicinal chemistry purpose, if you are using huge amount of palladium, irrespectively during the product formation some tiny amount ppm level of palladium will be left during the processing, even after running column and washing and every other processing you would like to do, ppm level palladium may still left behind, which will not be desirable if it is a drug molecule. No drug approval will be possible if decent amount of palladium is left. So, therefore, a desired reaction can be only considered industrially viable, medicinally viable if it requires very little amount of metal, for example, palladiums in particular. So, loading, catalyst loading decreasing to a certain level is essential for employing the reaction for industrial as well as medicinal purposes. We will discuss more on those issues in the next class. Till then, Let us look at the Negishi reaction. Let us read more example of the Negishi reaction, also the pros and cons of each of these coupling reaction. See you in the next class. Keep reading.